Swayam Prabha. Digital India. Educated India.
Now we have our next topic is graphic theoretic algorithm and computer programs. This is most important for AI and ML. That is why we started with fundamentals of graph theory, and based on that basic definition, let us going to discuss graph theoretic algorithm, and based on some flow chart. Once a person can understand the flow chart, can directly go to the program. So, to be able to use the digital computer in solving graph theoretic problem is undoubtedly an important part of learning graph theory. Especially for those interested in application, most of the practical problems which call for graph theory involve large graphs that are virtually impossible for hand computation. In fact, one of the reasons for the recent growth of interest in graph theory has been the arrival of the high-speed electronic computer. Problems that are hitherto were of academic interest only are suddenly being solved by the computer, and their solution are applied to practical situations. So, computer programs have been written to handle successfully large graph encoded into PET flowchart problem, transportation networks, electric networks, circuits layout and like. Now, let us start with algorithm. Now, algorithm is in the essence a recipe for solving a certain mathematical problem. It consists of set of instructions that we followed step by step will lead to the solution of the problem. Every step in algorithm must be precisely and unambiguously defined. An algorithm must terminate after having solved the given problem in a finite number of steps. So, as pointed out by the Nath of the books referred by Nursing DO, every algorithm must have 5 important features. One is finiteness, definiteness, input, output and effectiveness. So, these 5 points are important for designing the algorithm. So, algorithm can be expressed in a different for MS, right. Their steps may be written in English, it may be in the form of computer program written in complete detail in the language understandable by machine in use. Number 3, the algorithm may be expressed in the form between 2 extremes such as flow chart. Each form has a certain advantages and shortcomings. Usually an algorithm is first expressed in ordinary language, then converted into flow chart and finally written in the detailed and precise language so that a machine can execute it. Next, efficiency of algorithm. An algorithm must not only do what it is supposed to do, but must do it efficiently. So, the 2 main criteria for efficiency of an algorithm are the memory and computation time requirements as a function of the size of the input. In our case, the input is a graph and its size is the number of vertices n and number of edges e. For most graph problem, the memory requirement is generally not a bottleneck, but the computation time can be working for that. So, we saw the opening remarks of this chapter based on the computation time. So, in evaluating the figure of the merit of an algorithm, one may seek the worst case execution time, that is time taken for the worst possible choice of the graph of the given size, or the best case is execution time or the average case. So, often more than one algorithm is available for one graph theoretic problem. Sometimes one algorithm can easily be seen to be more efficient than others for all non-trivial graphs. In many cases, however, the relative efficiency can be compared only in the context of the size and structure of the graph, the detailed implementation of the algorithm detailed implementation of the algorithm and the computer used. So, the detailed analysis of the performance of a graph theoretic algorithm is extremely involved. We will not indulge in such analysis as that would require a chapter in itself. So, we will however make some gross observations on complexity of the algorithm, namely how the computation time grows as a function of n or e. As n and e become very large, assuming that worst case graph is provided as in the input, such an index of performance too unrealistic to be useful in estimating the expected computation time of the program is often valuable in classifying algorithm and their theoretical studies. So, a detailed analysis of the performance of the graph theoretic algorithm is extremely involved. We will not indulge in such analysis as that we would require chapter in itself. We will however make some gross observation on complexity of the algorithm, namely how the computation time grows as a function of n or e. As n and e become very large, assuming that the worst case graph is providing as the input, such an index of the performance too unrealistic to be useful in estimating the expected computation time of the program is often valuable in classifying algorithm and their theoretical studies. So, let us start with algorithm 1 based on the connectedness and components. Already we discussed what is the meaning of connected and components. A graph G is said to be connected if there is a edge between two vertices, and component mean taking a disconnected graph and have a subgraph that is also connected, then it is said to be component. So, that is already discussed. So, this you have to refer the previous talk. Now, we have to go the description. The basic steps in the algorithm is the fusion of adjacent vertices. We start with some vertex in the graph and fuse all the vertices that are adjacent to it. Then we take the fused vertex and again fuse with it all those vertices that are adjacent to it now. So, this process of fusion is repeated until no more vertices can be fused. So, this indicates that a connected component has been fused to a single vertex. If this exhausts every vertex in the graph is connected. Otherwise, we start with a new vertex and continue the fusing operation. So, this is the meaning of the description of algorithm. Further, mathematically you have to do with an adjacency matrix. The fusion of the jth vertex to the ith vertex is accomplished by OR ing, that is OR technique. 1 plus 1 equal to 1, 0 plus 1 equal to 1, and 0 plus 0 equal to 0, 1 plus 0 equal to 1. So, like that you have to do ORing, that is a logical adding the jth row of the ith row as well as jth column to the ith column, and the jth row and jth column are discarded from the matrix, and it is difficult or time consuming to discard the specified rows and columns. One may leave these rows and columns in the matrix and taking care they are not considered again in any fusion. So, note that a self group resulting from a fusion appears as a 1 in the main diagonal, but parallel edges are automatically replaced by a single edge because of a logical addition or ORing operation. These of course have no effect on the connectedness of a graph. So, a minimum number of fusion that may have to be performed in this algorithm is n minus 1, where n being the number of vertices. Since in each fusion one perform at most n logical addition, the upper bound of the execution time is proportional to n into n minus 1. So, this idea you have to know, then only you can get the algorithm ideas. Now, let us start with the flow chart. First read G graph, and we have a subgraph G equal to capital G, and we have a component, let it be C equal to 1. Select a vertex I in G, fuse all vertices and adjacent to I with I and call the new vertex I. Is the number of vertices is non-adjacent to I the same as before fusion? If it is no possible, then you go backtrack and do the process. If yes mean, delete from G vertex I along with all the vertices fused with I, call the remaining subgraph as G, and we have a condition, is there any vertex left in G? If you say yes, then go to C plus 1 component, lot of component will increase. If you say no, then print each C with the vertex and stop the iteration. So, this is the meaning of connectedness and components of a graph. So, a proper choice of the initial vertex in each component would improve the efficiency, provided one did not pay too much of the prices for selecting the vertex itself. So, the flow chart of the connectedness component shown in the figure. So, we can write the computer programming and ready to execute, and with the legend identification variable used in the program. Now, you can use C, C++ or Python, whatever may be the programming language, use it so that you can get it. So, the program select a vertex with the maximum degree at the initial vertex in each component. Now, we have a example, an input and a resulting output are shown in the as shown in the figure, as shown in the flow chart. The input is 20 by 20 adjacency matrix represent 20 vertex graph. The output is a list of component followed by the names of the vertex, include each component. So, vertex I is corresponding to the ith row and column in X. So, this is the things we have to do. So, this is the example. So, illustrate the program and an input resulting output as shown in the follows, and 20 cross 20 adjacency matrix represent 20 vertex graph, and the vertex I corresponding jth ith row and column in X. So, that the output will come for computational components of 1 is like that 6, 7, 8, 10, 16, 19, 20 will come. Similarly, we have a components of 2, 3, 4, 5, we have a corresponding entry will be coming in the output. So, this can do only computationally, manually very difficult task. So, this is the things we started, and this is the fundamental idea of reaching the A and ML of a sorting, agent and environment. These ideas already we come across, that we have to go further. Next, a spanning tree. A description of the algorithm is, let the given undirected self loop free, mean there is no parallel edges and self loop, and a graph G containing n vertices and e edges, and it labeled 1 to n, and a graph described by the two linear array of f and h, such that f1 in capital F and h1 in h are the end vertices of the ith edge in G. So, at each stage in the algorithm, a new edge is tested to see if either or both of the its end vertices appear in any tree formed so far. At the kth stage, 1 less than or equal to k less than or equal to e in the examining the edge. So, 5 different conditions may arise. Neither vertex fk or nor hk is included in any of the trees constructed so far in G. The kth edge is named as a new tree and its end vertices fk, hk are given the component number c after incrementing the value of c by 1. So, this is the things you have to do. So, we have a tree like that. So, here it span all the, either this way or this way you can go. So, if the vertex fk is some tree, so it is also a tree, and hk in a tree tj. So, the kth edge is used to join these two trees. Therefore, every vertex in tj is now given the component number of ti. So, the value of c is decremented by 1. So, in both vertices are the same tree. So, the edge Fk and Hk form a fundamental circuit, and it is not what it is not considered any further. So, you have a form a fundamental circuit, and if you join, this is one graph, if you have a what spanning tree from this, it covers all the vertices or the possibilities of connection of this you have to do. So, the vertex Fk is in the tree Ti and Hk is no tree, the Fk, Hk is added to Ti and assigning the component of the number Ti to Hk also. So, the vertex Fk is no tree and Hk in a tree Tj, the edge Fk, Hk is added to Tj by assigning the component of Tj to Fk also. So, this is a flow chart, read F, H, R, E, set k equal to 1 and c equal to 0, m equal to 0 is vertex Fx in any Ti. If you say no, then the vertex Hk in any Tj. If you say yes, include Fk and Hk in Ti and then connect with m equal to m plus 1. Suppose if the vertex Hk in any Tj is no, and then c equal to c plus 1 start, right, start a new tree Te with Fk comma Hk, and also we have to go to the next step m equal to m plus 1. Suppose is the vertex Hk in any Tj, no mean include Fk comma Hk in Ti, that also it reaches then m equal to m plus 1. Now, the vertex Hk in Tj is yes, if I and j are equal, there are two cases, one is yes and no. If you know, combine Ti and Tj of Fk comma Hk into one tree and c maps to c minus 1 and m maps to m plus 1. So, if you say yes, then m equal to m plus 1 increase, is m equal to n minus 1 or k equal to e, say no, then k equal to k minus 1 and process is going on. You say yes, print a spanning tree and forest and stop it. So, these are things we have to do for finding the spanning tree, or for a forest mean collection of lot of spanning tree in a graph. So, that is a forest. Spanning tree mean all the vertices start from n to f, v1 to vn, and it will form a tree, then it is said to be spanning tree, rest of them is a card. Next, minimal spanning tree algorithm. So, discuss in the section, we can use the algorithm suggested by Kruskal to find the shortest spanning tree in a graph, in which every edge has a distance or weight associated with it. This can be accomplished with the algorithm just described. So, the only additional work required is to sort the edge in a non-decreasing order of their weights, and before representing them by f and h arrays, it follows that the inequality must satisfy weight of the edge fi hi you calculate, and weight of the next fi plus 1 comma hi plus 1 calculate, check it out, these two weights, one is less than or equal to other, then we have to go to the next step. So, that is called as minimal spanning tree algorithm, or call it as Kruskal algorithm. So, because of sorting involved, Kruskal algorithm is not efficient as on the due to Prim's algorithm, because it is independently described by the Discross algorithm. Later on we are going to discuss, and no sorting of the edges, but builds up a minimal spanning tree by successfully connecting the partial formed tree in the nearest neighbor. So, now we have to go to the advanced languages like C, C++ and Python and so on, and this is what old one, and a listing of an efficient implementing of the Prim's algorithm, minimal spanning algorithm. So, the computation time of the algorithm is to n square, and n being the number of vertices. So, minimal spanning tree has been found quite useful in providing a lower bound on the length of the travelling salesman problem. Next, spanning tree with the desired properties. Instead of shortest spanning tree, one may wish to find the longest spanning tree, or one may interested in trees with other desired properties and constraint, such as spanning tree with a specified maximum degree or diameter, and the algorithm with appropriate additional sorting or testing can be used and such a purposes also. Next, description of the set of fundamental circuits. Here also we edge in tested to see if it form a circuit. So, with the tree constructed so far, but instead of taking the edges themselves in arbitrary order, was done in the algorithm to, we select a vertex Z, examine this vertex by looking at every edge incident on Z. Vertex Z, as we shall shortly see in the vertex added most recently in the partial formed tree. So, let the vertices of the given connected graph G equal to V comma E be labeled 1, 2, 3 and so on n, and the graph be given by its adjacency matrix X. Let T be the current set of vertices in the partially formed tree, and W be the set of vertices that are yet to be examined, and initially T equal to MT and W equal to V, the entire set of vertices can be designed. Next, we start the algorithm by setting T equal to 1, the first vertex, and W equal to V. Vertex 1 will be regarded as the root of the tree to be formed. After initializing, the following procedure is used. Number 1, the T and W, right, the first vertex, and W is what corresponding V, their intersection is empty, the algorithm is terminated. If T intersection W not equal to empty, choose the vertex Z in T intersection W. So, examine Z by considering every edge incident on Z. If there is no such edge left, remove Z from W and go to step 1. If there is an edge Z comma P, test if vertex P is in T. If P in T, find the fundamental circuit consists of edge Z comma P together with the unique path from Z to P in the tree. Delete edge Z comma P from the graph and go to step 3. If P in T, add edge Z comma P to the tree, the vertex P to set T, delete Z comma P from the graph and go to step 3. So, this is a technique we have to apply for the fundamental circuit. Okay. So, as mentioned earlier, the only tricky part in the algorithm is in step 5. So, how do we find the unique path from Z to P in the tree? The following procedure provides an answer. So, we maintain the push down list TW equal to T intersection W, which stores those vertices in the tree that have not been examined. The most recently added vertex is in the top of the stack. Each time a vertex is taken for examination, it is taken from the top of this stack and is removed from the stack. Two linear arrays of length n are employed, level I being the distance of vertex I from the root of the spanning tree, and PRD mean predecessor of I being the vertex V, such that I comma V is an edge in the tree with the V nearer the root. In other words, the predecessor of I is the predecessor of I, or of I is the path from the root to I. Check it out, level I equal to -1 if and only if vertex I is not in set T. So, the current set of tree vertices initially level 1 is set to 0 and level 2 is level of I equal to -1, where I varies from 1 to n. So, this is a technique you have to use it. Already we discussed the directed graph with the predecessor and successor, and using that idea and degree of Vi moving from one to another is 1 and back is -1. So, in the step 5 vertex Z is under examination and an edge Z comma P has been found such that vertex P in T, and to find the fundamental circuit found by Z comma P with the tree. So, we trace a unique path from Z to P in the tree by successfully finding the predecessor of Z, predecessor of Z and so on till we encountered predecessor of P. The predecessor of P is another word, is a fundamental circuit formed in the figure 11.4. So, this is the one. You start with the root, right, and unexamined vertex Z and check it out, the vertex being examined, and if there is a connection, generation of the fundamental circuit, unexamined vertex is this, and then vertex being examined here, and check it out, the predecessor of Z, and after checking this you go to further proceed. So, predecessor of Z. So, let it be P times of predecessor of P, you have to do that, and corresponding 1 to 2, 2 to 3, 3 to 4, like that you have to form the connection from one vertex to another vertex, and if not, you go to the which path is it comes, that you have to do that, and examine all the vertices, and finally one graph will come, that is called it as a fundamental circuit. So, this is the structure of the fundamental circuit graph. This way we can find the path. So, this it will be helpful for sensor. So, generation of fundamental circuits will be helpful for the sensor. So, this is a technique we are using, sorting and everything. Now, the most important things to note that predecessor of K of every vertex K in T of the vertex which is either already examined, and if K belongs to T intersection W, then predecessor of K not in W but predecessor of K in T. So, the flow chart of the algorithm is given in the figure and ready to be executed, and now you can do any program provided the end of the chapter. So, the execution time is bounded by n power nu, where nu lies between 2 to 3. If you say V, then V lies between 2 to 3. The value of V depends on the structure of the graph and also the labeling of the vertices. So, this is the flow chart, read n comma x, initial TW equal to 1, level is -1, level of 1 equal to no connection 0, and we have a question is TW equal to empty, and if you say if it is yes, stop it, and otherwise you have to go to the next no. No mean top of TW, pop TW is Z row all zeros. If yes, then go back, is TW is empty or not. If you say no, pick an edge Z comma P and corresponding entry XP equal to -1, and then if you say yes, add Z comma P to the tree, path P in DW, and the predecessor of P, level of P and the level of Z is 1. And if you say no, we form the fundamental circuit Z comma predecessor of Z and so on, and then it reaches the final stage because all the entries successfully proceed, then stop it. So, this is a theory of algorithm of fundamental circuit. Next, cut vertices and separability. Suppose you have a graph, right, there is a edge connection between the vertex V1, V2. If you disconnect, then we have a V1, V2 is a disconnected graph. So, this is a cut vertex and the graph set is separated, therefore, it is a separability. Now, based on this we have to form a algorithm. If we generate a fundamental circuit one by one and each fundamental circuit is generated by the label, all is edge identically using the following procedure. So, we will have identified the blocks in the graph. Now, each edge in the fundamental circuits is labeled with the 2's. When the second fundamental circuit is found, it will have either all the edges unlabeled or some of its edges would be labeled 2. In the former case, label every edge of the second fundamental circuit with the 3's, and in the later with the 2's. When this process reaches in the mth level, Therefore, 1 less than or equal to m less than E minus n plus 1 fundamental circuits. So, we may find any one of the three conditions. Number 1, every edge in the mth fundamental circuit is unmarked and label all of them with a new integer q plus 1. Some edges in the mth fundamental circuits are marked u and all others are unmarked, and label unlabeled ones as u also. Suppose the some edges in the mth fundamental circuit are marked u and others v and others w and so on. Let u is less than v less than w and so on, then relabel all the edges marked v, w and so on in G as u and label all unmarked edges in the mth fundamental circuit u also. So, these are steps you have to do, and when this process terminates, after having generated fundamental circuit, label the edge in each of them, and the following has been accomplished. So, every edge that belongs to a circuit has been labeled. Moreover, any two edges have the same label if and only if they are together in the same circuit. In other words, each set of edges carrying the identical label constitute a block. If there is a more than one block in the graph is separable. Any vertex incident on edges with the different labels in the cut vertex. So, an edge that has not been acquired any label in the bridge. So, the bridge is an edge whose removal disconnects the graph. So, in this algorithm, an edge belong to the circuit gets relabeled many times and obvious sources of inefficiency, and improvement suggested by pattern reduces a relabeling of edges by the following devices. Instead of relabeling the edges in a fundamental circuit as soon as it is generated, we wait till a vertex z in algorithm 3 has been completed examined and then assign identical label to the fundamental circuit thus generated. Therefore, labeling has to be performed only n times and not mu times. Moreover, we need not label every edge in the graph. So, it is left for the reader to construct a flow chart for the block identification algorithm in which algorithm 3 is completely embedded. So, using an entire different approaches, Ofcott and Torgen have given an algorithm which is faster than the algorithm described here is types of graphs. Their algorithm uses depth first search on the graph, and the graph is to be input in the successor listing form. So, its execution time is proportional to E, whereas the time bound for the read pattern algorithm described here is proportional n power nu, where 1 less than or equal to nu less than 2. Depending on the structure of the graph, analysis and executive tests show that the typical graph of n vertices and E edges. So, Ofcott and Torgen's algorithm outperforms pattern algorithm as long as E is less than or equal to phi n for graphs of much higher densities. Pattern's algorithm performed better. Thus, for planar graph for E less than or equal to 3n minus 1 of the faces, Ofcott and Torgen's algorithm will generate B faster, and typically for an 80 vertex 400 edge graph, the IBM 7044 took about 7 seconds for block identification with either of the two algorithms. Next, directed circuits. So, the description of the algorithm is first proposed by Roberts and Force and subsequently systematized by Ternan, uses an executive search to find all the directed circuits in a given diagram G. So, as usual, the vertices of G are assigned at 1 to n and their names. So, the algorithm depends on starting from a vertex P1 and building the path P1, P2 and so on Pk until no further vertices are available at vertex Pk. At Pk, when it is not possible to extend the directed path any further, the algorithm check to see if there is a directed edge from Pk to Pv. If there is such an edge, directed circuits P1 to P1, P1, P2, P3 and so on P1 has been found and is duly recorded. If there is no such edge in the diagram, we move back to one vertex to the Pk minus 1 and try extending the path from the pk minus 1 along the different edge, whether a directed circuit is found or not. So, the algorithm makes vertex pk forbidden for the next expression from p suffix k minus 1. So, this process of looking for directed circuits and then moving back to vertex to continue till we finally backtrack to the vertex p1 itself. Thus, all directed paths starting from p1 have been examined and directed circuits recorded. Starting with the next vertex, the entire process is repeated. So, the iteration starts with vertex p1 equal to 1 and ends with p1 equal to n. So, this is the meaning of how to find the directed circuits in a given digraph. So, these are all the executive search for directed path. We must take the following precautions. Number 1, in the process of extending each directed path, going round and round, a direct circuit must be avoided. This is achieved by insisting that any vertex that has already been included in the directed path is not available for extending the path. Generating a directed circuit of q vertices in q times, once at each vertex in the circuit must be avoided. So, this is accomplished by insisting that no vertex I less than or equal to p1 is available for the path extension. If the path begins with the vertex p1, this rule assures that the search for the particular directed circuit commences only when its lowest number vertex is at the path initiation. Third point, the same path must not be considered more than once during the path extension. So, this is accomplished by keeping the updated list of the forbidden vertices in a binary n cross n matrices and H is equal to Hij. So, the one entries in the ith row corresponding to the vertex that are forbidden from vertex I, and if the vertex j is a forbidden from vertex I and Hij equal to 1, if 0 entry indicates that the vertex is not forbidden, Hij equal to 0, then the vertex j is not forbidden from vertex I. So, the matrix H is reset to 0 each time new vertex is chosen as a starting vertex. So, this is the execution of the searching of the directed path. So, the directed digraph is inputted and its adjacency matrix, and we already saw. So, the vertex are labeled as usual in the integers 1 to n. So, the directed path considered represented by the linear array is p1 to p2, p2 to and so on pk minus 1 and pk minus 1 to pk, and there is no path 0 0 you put it of order n. The first vertex of every path is p1 and the last one is pk. So, these things you have to do, you start from the vertex 1 and then vertex 2 if there is a connection, and 3, 4, 5. Now, the algorithm can be best explained with example. When applied to the digraph, the above one, the following will be performed. Now, we have a totally how many paths? 5 paths. Let us start with P1. Now, P1 to P1 the point you take it, right? P1 to P2, there is no path up to P5. Now, you start with P1 and P1 to P2, right? Then there is 2 ways to do that. One is towards 2 and another is 3. Therefore, 2, and then rest of them P3, P4, P5, P6, no path. Therefore, 0, 0. Next you take start from 1 and go to the either 2 or 3, therefore 2, and then further 1 to 3, 3 to 4, and 1 to 2, 2 to 5, right, and 1 to 2, 2 to 4, 1 to 3, 3 to 1 to 2, 2 to 4, right. There is one path. Therefore, P2 exists. Therefore, 1, 2 will come. Next, 1 to 2, 2 to 4, 4 to 5, right. Therefore, we have what? And then 5 to 2. So, we have a 4. Therefore, 1, 2, 4 will come, and start with how many 4 paths? No 4 paths and no 5 paths. Therefore, 0, 0. So, here you see that 1 to 2, 2 to 4, 4 to 5 and 5 to 2 there is a circuit form. Therefore, what set H, report the circuit, set H43 equal to 1. So, this is a way you have to take the action. Now, you go to the next 1 to 2, 2 to 4, 1 to 2, 2 to 4, therefore 2, 1 to 2, 2 to 2 to 5, that is also 2, and then 1 to 2, 2 to 4, 4 to 5, 5 to 2, therefore there is no possibilities, therefore 0 0 rest of them, therefore no circuit H451. So, this way you have to go to the next round. Similarly, you have to go to the other 1, how many 2s, how many 3, how many 4, like that. How many path P1, P1 mean 1 path, P2 mean 2 path, P3 mean 3 paths, 4 paths, 5 paths. So, let us go with this direction of this ideas. Okay. So, 1 to 2, 1 to 1, that is 1, 1 to 2, 1 path, 2 path, 1 to 2, 2 to 4, 2 paths, then 1 to 2, 2 to 4, 4 to 5, and then we have another way is 1 to 2, 2 to 4, 4 to 5, 5 to 2 and 2 to 4. Once again it will come the what circuit, right, but the execution is forming the same circuit, therefore 1 to 2, 2 to 4, 4 to 5. So, this will come. So, like that you have to go the all possibilities. Next 1 2 4 0 0 will come, that is H41 to H42, H43, H44, H45 and then stop. Next H24, H24 is 1, therefore like that. So, this is a way we have to go, for no circuits will come. Similarly, 1 to 2, 2 there is no further proceeding, and then 1 to 5 0 0 no circuit form, 1 to 0 0 no, so H21, H21, 22, 23, 24, 25 and then stop it. So, there is 1 to 2, only 1, and then there is only one point from the we can stop it. So, this is the things of the first set of path we have to deduct. Similarly, start from 2 and go the same methodology, sorting of one path to the another. First you take 2 and how many paths from 2, and we have to go next. So, report 4 3, 4 3 we have a circuit 1 2 sorry 2 4 4 3. Next third vertex, no third vertex you see you start only self loop, therefore stop it, and then fourth vertex we have 4 to 5, right, 4 to 5, that is all, and then 4 and 4 stop it, 5 only point no circuit, therefore stop it. So, this is a technique of what using the directed circuits, how to form using this diagraph.